my name is Ansh Gupta, and today I want to take you on a little tour of the night sky. And so today's presentation is basically going to be in three parts. First, I'm going to tell you a little bit of history about how astronomy got started, and then I'm going to walk through some of the most cutting-edge discoveries in the field right now, things that the top-cut astronomers are working on. And then finally, if time allows, I'll delve a little bit into my own research and tell you all what I've been working on in my undergraduate career so far. So let's go ahead and dive right into it. When I see an image like this, I'm filled with wonder. If you went back to before the invention of the telescope and asked the most preeminent writers of fiction to conjure up a picture or a painting as spectacular as they could imagine, I doubt that you could come up with a single image as great as the ones that we see coming in on a weekly basis from telescopes like the Hubble telescope and the recently launched James Webb Space Telescope. These images fill me with a sense of discovery, curiosity, awe, wonder. They make me wonder about the mystery present within our universe that seems to pervade its every deepest corner. And when I think of how incredibly curious this all makes me and the deep sense of wonder I feel, I can't help but think about how the earliest humans must have felt looking up at the stars, seeing the same sights that we see today without even close to a sliver as much of the scientific knowledge and understanding. It must have seemed like pure magic to them. So I'd like to go back in time a little bit and try to convey those feelings to you. Now, if you walk outside tonight, you might see a sky that looks something like this. Pretty amazing, right? Not so much. Maybe if you're lucky, you'll see something like this. But if you venture far from the cities, away from the pollution of lights, street lights, businesses, homes, the sky becomes darker and darker, and the stars in our Milky Way galaxy pop out of the darkness, seemingly like magic. This is the night sky view that was afforded each and every single night to humans for hundreds of thousands of years before the development of electricity. Imagine going to sleep every night and seeing this as your last moment. I want to talk a little bit about why prehistoric people engaged in astronomy. Besides marveling at the wonder, you can imagine the earliest humans had bigger things to worry about, perhaps some more important things on their plate. But there were some very key reasons to engage in astronomy for these earliest peoples. For one, they had timekeeping. They needed to know what time of day it was. It wasn't as perfect. It wasn't as important to be exact, but it was important for them to have some general sense of timekeeping. Alongside this, knowing what season it was pretty important. And to us, it might seem obvious. In the winter it snows, in the summer it's hot. But having a more precise view of the seasons is actually pretty important, given the migration patterns of animals, hunting and gathering, and especially for the development of the earliest forms of agriculture. Knowing the positions of the planets and stars was also of importance to people throughout the centuries and millennia, just out of pure curiosity, and also because of additional reasons. For these people, they didn't have the internet, they didn't have phones, they didn't even have books. All they had were the stories they made and told themselves. And to people back in time, the night sky was an illustrious picture book on which they painted their stories. And so the movements of the planets and stars, breathtaking eclipses, all served as facets of their mythology, their religions, and their culture. And so let's talk about some prehistoric astronomy. Prehistoric here means before the development of written language. And so we know these people practiced some form of astronomy, but most of what we know must be inferred because they didn't leave us any writings to draw from. These are some of the earliest known possible indications of humans engaging in astronomy. These are pieces of bones from mammals. On the left, it's actually a bone from an unknown mammal species. On the right, bones from a baboon. And they're marked in a very particular way. Now, there's lots of debate in the scientific and archaeological community about this, but some scholars have indicated that the markings on these bones correspond to cycles of the lunar calendar. For example, the bone on the right has 29 notches on it. 29 days is approximately the length of the orbit of the moon around the Earth with respect to the sun. It's the distance between two full moons, or two new moons. So perhaps these early people had some, or attached some significance to the phases of the moon and kept records. But we don't know. For example, the bone on the right is actually broken. So some archaeologists have proposed that perhaps there were more markings. And so these are uncertain. But as we move further, we find incredible instances where we know these people engaged in cutting-edge astronomy for the time. For example, in Warren Field in Scotland, we see a series of pits, 12 pits. It's kind of bright on the screen there. Anyways, so the people at Warren Field carved out 12 deep pits, and nearby we find poles that were inserted into them. Now what's remarkable is that these pits are aligned in such a way that at the longest day of winter, the pits are aligned exactly with the position of the rising and setting sun. Now that alignment could be by coincidence, and yet time and time again, across cultures, across continents, we see the same alignment repeated. The longest day of winter, or the longest day of summer. They built their structures aligned to these points to mark a changing of the seasons, going from the first half of winter to its second half and drawing towards a more prosperous time. And it's hypothesized that these pits and the poles that were placed within them could be markers of the months, perhaps an early lunar calendar system. Here at the Goseck Circle in Germany, we see an even clever and even more precise design. On the day of the longest winter, it's hard to see on the screen, but the building was constructed such that the light from the sun would precisely move through openings at the beginning and at the exit of the building, corresponding to the positions of the rising and setting sun.
I'll come over here and point it out since it's not really showing up on the screen. But when the sun rises on the longest day of winter, it's aligned exactly at this angle, just threading through this passage, the center of the auditorium, and then when the sun sets, it just exits through this line here. So definitely not a coincidence.
In China, in Taosi, there's an artifact known as a gnomon there. A gnomon is a type of sundial. In fact, it's the piece of the sundial that actually casts the shadow. The base plate is not found, so we don't know whether these people made accurate clocks, but we know that in this place in China, they were using some sort of sundial to indicate relative or rough times of day. And to me, most fascinatingly, interestingly, and perhaps most impressively, were the ways that the Polynesian people navigated for millennia. The Polynesian cultures throughout the Pacific Islands were able to navigate for thousands of kilometers just using the stars. They had precisely memorized the positions of stars, our Milky Way, and other celestial objects throughout the sky, and were able to travel thousands of kilometers to various islands. This is a recording from Captain James Cook in the 1700s of a tale told by a Polynesian sailor named Tupaya. Now, of course, this is a lot later than the earliest navigators, but Tupaya was able to, from memory, note exactly the position of at least 74 islands, separated by 3,000 kilometers, just from memory, and Tupaya was able to navigate all these islands just by his knowledge of the stars above. And these secrets were passed down in oral tradition for thousands of years. It's absolutely amazing and incredible that this was just a common skill for people to have, just to look up at the sky, know exactly where you are, and to be able to sail on a journey, going for days and days, not knowing where you are, and yet ending up exactly where you wanted to go. Now we move into the realm of ancient astronomy. Ancient meaning now we have actual written records of what was written down. The first written records we have of astronomy comes from Mesopotamia, the Fertile Crescent, in what's now modern-day Iraq. The earlier civilization of Sumeria, we don't have any extant writings from, but the later civilization of Babylonia recanted and recycled their writings. And so we know in early Sumeria, they used a numbering system that went in 60s. The counting system we use goes in tens, 10, 100, 1,000, but actually in Sumeria and Babylon, they used a base 60 system. And we see artifacts of this in our math and astronomy today. For example, 360 degrees in a circle. They created some of the earlier star charts that we have any knowledge of. And also, Babylonian constellations are the basis for many of the later ones that were used by the Greeks and in Arabic culture. And they were also able to track future eclipses. Imagine for thousands of years, for hundreds of thousands of years, as an early human, you would suddenly see on some rare occasions the sun supposedly or apparently being gobbled up by the moon. The whole world is cast in darkness, the animals are going crazy, the crickets start chirping, everywhere around you is cast into darkness in the middle of the day, and it seems as nature is turned upside down. And yet, in 4000 BC, as early as 4000 or 3000 BC, people were able to make sense of it using math, science, and physics. Egypt had very sophisticated astronomy as well. The famous Great Pyramids were aligned with the pole star of the time. Now, many of us know that the North Star, Polaris, points directly north. Now, it turns out that stars move in the sky over time, some slowly and some more quickly. And so back at the time of the Great Pyramids, there was a different pole star, and amazingly, the directions of the Great Pyramids exactly point to where this pole star would have been at the time. And also the entrances to the Great Pyramids are aligned with the winter solstice, the longest day in winter. Again, it's similar as we saw with prehistoric monuments. People used basically structures as calendars to know which part of the year they were in. Are you in the first half of winter? Are you finally approaching the end? And they also had a sophisticated calendar, which was marked by the rising of Sirius, the brightest star in the sky. It's interesting, as we go through this presentation, you'll see several different systems of calendars, aside from the one that we use currently, based on all sorts of astronomical objects. And it makes you wonder, people back then had such accurate calendars, and it's partially through coincidence that we ended up using the system we do today. It's interesting to think what things could have been like, what significance we would have placed on different celestial objects. The Mayan people of Mesoamerica had quite an interesting calendar system in that vein. Of course, famously, the Mayan calendar was reported to end in 2012, and a lot of people had predictions that the world would end as well. It turns out that the Mayan calendar is actually cyclic, and so instead of an ending, it just signaled a new beginning of the calendar. Now, the Mayans had detailed tables of the phases of the moon extending for decades. They could predict eclipses and the rising and setting of Venus. Now, Venus was of critical importance to the Mayans. They called it the evening star. And some Mayan calendars and some Mayan astronomers attempted to build a timekeeping system not around the sun, a solar calendar like we use today, not around the moon, a lunar calendar, as is used in many cultures even to this day around the world, but a calendar based on Venus, a truly unique feature that has not been seen in any other culture since. And the Mayans were able to calculate the precise cycles of planetary orbits. They assigned meanings to the planets related to gods and their religion, and they were able to precisely tell when the planets would be up and when they would be visible in the sky. In India, the earliest traces of astronomy are from the Indus Valley civilization, where we see some of the earliest calendars through indirect evidence. However, we have no recorded, at least no surviving records, written records from that civilization. And so later on, we see the first direct written evidence of Indian astronomy. They had calculations for the motions of all kinds of different celestial objects. They could figure out when two planets would come as close as they would before drifting away again. They could predict eclipses far into the future. And many Indian astronomers were able to calculate with extreme precision, the best of the time, and within just a few percent of their currently accepted values, the periods of planets, the tilt of the Earth's axis, the values of pi, and so on. Now, what I find interesting about this is that they were able to get such accurate values for all of these constants, despite the fact that every culture we've talked about so far has assumed a geocentric model. Back in history, it seemed like the Earth was the center of everything. I mean, I don't feel like I'm moving, thousands of kilometers per second around the sun. I feel like I'm pretty stationary, and it seems like the sky is moving above me. So, for all of history, that was the natural assumption. And it would only be until much later that it was challenged. But I find it personally fascinating that so many civilizations, with this critically wrong assumption, were able to basically proceed as though everything were correct. They were getting correct constants, correct predictions, and you could kind of see, if you were in their shoes, why it would be easy to settle into this narrative. And this is an example of an Indian calendar tapestry on the right there. Now, Chinese astronomers were they're astronomers from which we have some of the most surviving written records. They kept extremely detailed records of their observations, and so we have lots of logs from China talking about stars and other celestial objects. They were also, like many cultures before them, were able to predict the precise timings of eclipses. From China is where we see the first ever star catalog, a list of stars, their positions of the sky, their colors. This is something we take for granted now as astronomers. I can pull up a website called Sinbad and look up any star in the sky that's ever been imaged and see a picture within seconds. And yet in these times, you could look up and see stars, but very few people had actually written them down and thought to catalog them. And amazingly, it was only the Chinese civilization that recorded and wrote down their observations of the supernova that produced the Crab Nebula. That's a picture of the Crab Nebula there. You may have seen it before. It's a very famous image, spectacular sight to see through a telescope. Now what's amazing is that this nebula was produced by a supernova. So when an extremely, extremely massive star, many times the size of the sun, nears the end of its life, its core runs out of fuel. The core supplies the pressure that holds it up its collapse from gravity. But when fuel runs out, the star collapses, and it gets bunched up and tighter, and all the material starts falling to the center. But all of a sudden, as this accelerating mass hits the center of the star, it bounces off extremely energetically as the whole core of the star is crunched, and its outer layers are thrown out in a violent explosion called a supernova, which sometimes releases more energy than the entire sum energy of a galaxy, which can have billions of stars. A single flash, this one supernova, can outshine 1 trillion stars. And this supernova was visible to astronomers on Earth. And it wasn't faint, it wasn't an object that you might miss if you didn't look closely. This was the third brightest thing in the entire sky for 2 years after the sun and the moon. And it was visible during the day. So imagine looking up imagine looking up right now and seeing a supernova, a flash in the sky, a spread of gas and dust. It's truly amazing. I can't imagine anything like that. And I hope that by some miracle, one of the stars that is unstable, Betelgeuse or something, goes supernova and we're treated to a truly cosmic show, even though the odds aren't great. Now, of course, when you think of ancient astronomy, your mind naturally goes to Greece, and for good reason. The Greeks took a very interesting approach to astronomy. They really applied a lot of mathematical rigor to it and turned it into a true science that we consider it to be today. So they created amazing mathematical models based on nested spheres. The Greek model of the universe, while there were many, the one that the most people believed in was essentially that the Earth was at the center and all the other planets were attached to spheres which were rotating around the Earth. These spheres were made out of a material called ether, and all the planets were attached on them as fixed points, rotating, almost like a classroom stellarium. Now, amazingly, even some of the Greeks disputed this model, and Aristarchus, the Greek astronomer Aristarchus, was the first to propose a heliocentric model, with the sun at the center of the universe. Not fully correct, we now know there is no center of the universe, but so far advanced and so past his time. The Greeks were also able to make astonishing predictions. They measured the circumference of the Earth to within 5% of its currently accepted value. Amazing. No one had ever been able to truly encapsulate the size of the Earth. I mean, think about it. How would you even go about measuring such a thing? And one of the most impressive pieces of physical machinery that has ever been discovered in history is the Antikythera mechanism. This is a piece of mechanical clockwork that was discovered in the 1900s. And at first, it just kind of looked like a chunk of metal. As we looked closer, we noticed that there seemed to be some kind of gear on the outside. And so scientists probed deeper. They used a technique called X-ray crystallography, which allowed them to probe the inner structure of the mechanism without breaking it or disturbing it. And they investigated the very inner crevices of this device. And what's astonishing is that this was one of the first analog computers. This is a computer. It doesn't exactly look like a Windows, maybe a Linux. So this computer basically had a series of gears, whirs, and knobs, and it allowed the Greeks to calculate immediately the future positions of many celestial objects, the moon, planets. It told you the future times of eclipses. Amazing, a computer. Now, the so-called Aristotelian understanding, basically this view of the Earth at the center with spheres surrounding it, started to come under question when we saw some weird observations. So one of the things we started to notice was this so-called retrograde movement of Mars. And this is actually something that people had been observing for many, many years, possibly for millennia. But people had just kind of glazed past, maybe we were misseeing, or they just kind of brushed over it. Because of course the Earth has to be at the center. I mean, it just seems so natural. The retrograde motion of Mars is caused by the fact that Earth and Mars orbit around the Sun. And Earth orbits faster than Mars. And so as we pass next to Mars, you can see the picture of Mars projected on the sky for us normally appears to move in one way, as either Mars moves or Earth moves. But as the Earth kind of catches up to Mars and overtakes it, for a moment, Mars appears to stop in its progress across the sky over the weeks, move backwards before returning to its normal motion. Retrograde motion, retro against. And so a pure heliocentric model cannot explain this. It simply can't. And the Greeks loved science, and so as much as it distraught them, they couldn't keep their perfect celestial spheres. And so the Greek and Egyptian astronomer Ptolemy came up with a system called epicycles. This bizarre system on which all the planets still orbited Earth, but not directly orbiting the Earth. The planets, such as Mars, orbited and circled around a point which orbited the Earth. Okay, very strange. You can see there, basically Mars is orbiting an invisible point in space, which is itself following a circular path around the Earth. And amazingly, as weird as it seems, this kind of motion could actually explain the observations, which is so interesting to me. They had such sophisticated mathematical machinery that they were able to come up with this convoluted system, which actually worked. But other cracks began to show, and we started to see some revolutions in astronomy. Before I move on, does anyone have any questions on that segment? Okay, great. So one culture that I feel often gets overlooked in the history of astronomy is the Islamic Golden Age, or the Islamic world, essentially. And this was during the reign of the Abbasid Caliphate, when the Islamic world was experiencing a golden age, and indeed, astronomy experienced a great flourishing during this time period. And so this culture created extremely detailed star catalogs. They created some of the most precise instruments that were used to find and navigate using the stars. And in fact, they had such detailed catalogs that 2/3 of stars that are named today have Arabic names. I don't know if you guys knew that, but when I found that out, I was amazed. We also see the first recorded descriptions of the Andromeda Galaxy. The Andromeda Galaxy is visible by the naked eye, so there's no single person discovered it. Everyone could see it, but it was first described and written down in this time period. And then we move on to the Copernican revolution. Finally, the view of heliocentrism prevails. So the astronomer Niccolò Copernicus proposes this model after seeing lots of different kinds of observations. The epicyclical model is able to explain some things like retrograde motion, but there were cracks starting to form. And this was primarily because we started to notice things like the planets having elliptical orbits. They weren't perfectly circular. And we started to see, eventually we saw things that just obviously ruled out the model as a result of the invention of the telescope. But before that happened, there was an astronomer named Tycho Brahe who had essentially tracked the positions of planets very closely, and his student Johannes Kepler started to notice that as you analyze the data of where the planets are moving, they're not perfect circles. They're pretty close. Most of them are pretty close to circles, but they deviate just a little bit. And Kepler had no idea why this was. I mean, for literally hundreds of years, everyone just kind of took Aristotle's word for it, that the planets orbited in these circles. And yet he did the math, and he figured out they were actually orbiting in these shapes called ellipses. And so he came up with the so-called 3 laws of planetary motion, which describe how the planets move through the sky, that we still use today to calculate all sorts of things, from the mass of black holes at the center of galaxies to the period of rogue planets and their possible sizes. And so Kepler introduced these laws, but we still didn't know what caused them, and that would take a while longer. But here we see finally the invention of the telescope with Galileo. Now Galileo, contrary to popular belief, did not invent the telescope, but he did popularize it. Telescopes were actually invented by opticians in the Netherlands. And even today, some of the best and most powerful optics in the world are produced there. And so Galileo was actually, his importance to our story is essentially that he was an early proponent of telescopes. He spread their message far and wide. And interesting, in a kind of a correlation between astronomy and the military, the way he essentially campaigned for the distribution of these telescopes was by going to various leaders of Europe and saying, these telescopes can do so much for your military, you can see ships coming away at shore from miles away. And so he convinced lots of European leaders to mass produce these telescopes, and that allowed him to do his science too. And so Galileo was the first to observe the phases of Venus. Just like the moon has phases because it orbits Earth, Venus itself has phases. And this is only possible if Venus orbits the sun. And so this was kind of the final nail in the coffin for geocentrism. Many people had been converted to Copernicus' side, but after Galileo observed the phases of Venus, and especially after he observed the moons of Jupiter, that was kind of the last straw. Because Jupiter's moons, he literally directly observed orbiting Jupiter. I mean, it's not going around the sun. And if these moons are going around Jupiter, I mean, what's to say that all the planets aren't going around the Earth either? Now, there was one problem with these early telescopes, is that they were called refractors, which means they used big lenses to basically bend the light towards the eyepiece. So a telescope is like a big bucket of light. It's round and it collects all these photons coming in, and lenses focus that light. But the problem is, if you want to have a really nice telescope, you need to build it really big, because these lenses, in order to focus these lenses, you need to make them wide, right? You want to collect more light and see fainter objects, so you want to make your lenses wide, but wide lenses are very heavy and they focus far away. And so you started to see telescopes that were being built that were like tens of feet long, these monstrous telescopes that were completely unwieldy, unmaneuverable, and expensive. And so that's when Newton comes in and kind of revolutionizes everything in multiple ways. So for one, he invented the first reflecting telescope. By using mirrors, you eliminate the need for lenses, or you can use lenses and mirrors together. Now the advantage of mirrors is that they bounce light, and so instead of having huge lenses all stacked on top of each other to try to focus light, you could just use a few mirrors, and the light would bounce between them and focus up that way, which is a very awesome invention. Newton also came up with calculus and finally gave us a reason for why planets orbit in the way they do. For literally millennia, people didn't know why the planets orbited. People had tried to come up with explanations, rotating spheres, some kind of electromagnetism, but nobody knew. It was a complete mystery. And finally, Newton came up with his theory of gravity and explained the orbits of the planets. So what's amazing is that Newton did a lot of this while he was in his summer home during the Black Plague, so hopefully you guys had a bit more interesting of a quarantine project than that. And then now we're kind of getting into the more modern history of astronomy, where we start to polish up our understanding of the solar system. So the astronomer William Herschel of England discovered the planet Uranus in 1781. And Neptune was found by a relatively unknown astronomer named Johann Gottfried Galle in 1846. And what's special about Neptune is that this was the first planet that was predicted mathematically before it was observed. So since ancient times, we had known about the 6 planets. I mean, they didn't know that Earth was a planet, but they obviously knew about it. And then they knew about Mercury, Venus, Mars, Jupiter, and Saturn. Those are all visible by the naked eye. And then only in 1781 did we discover Uranus. Neptune, we didn't directly observe first, but what astronomers did is they looked at how it changed the orbit of Uranus. So as astronomers started to, watch Uranus over the course of decades, they saw its orbit didn't look quite right. There's something off about it. And so people started to realize if there was this mysterious planet that was further away that we hadn't even observed yet, but if there was this planet, a gas giant, that was outside of the orbit of Uranus, it would actually tug on Uranus slightly. It would speed it up at some points and slow it down at other points. And so people basically came up with a mathematical table and did all the physics, and they figured out where would this planet be, and lo and behold, they pointed a telescope there, and there Neptune was. Pretty amazing stuff. They tried to do the same thing for Pluto, but it took a lot longer. It took several more decades because Pluto is just a little bit finicky. It's a little small, which is why it's not a planet. Anyways. And finally, we get into really, truly modern astronomy. So one of the most revolutionary inventions for astronomy, and pretty much ever, is the photographic plate. Now, all this time, we had these telescopes, and They were amazing. We could see fainter things than we ever could before. You could zoom in and make out details. But you were still limited to the human eye. I mean, someone had to go and literally look through the telescope and pretty much sketch out what they were seeing. So if you wanted to tell someone else what you saw or what it looked like, you'd have to sketch it out. That was like the best case scenario. Photographic plates were a type of equipment that you could put at the eyepiece of a telescope, and the light would actually expose the plate and create an image. This is amazing. Like, for the first time, you could show someone else what the stars look like. So that's amazing. But also, they allow you to take long exposures. Your eye just sees things how bright they are. But you could put a photographic plate at the end of a telescope and take a picture for minutes, hours, sometimes even days of time, and stack light on top of each other and see fainter things that could ever be seen before. We also see the invention of spectroscopy, breaking the colors of the light up into the rainbow. Now, why spectroscopy is important is that it allows us to basically turn our telescopes into a full-blown lab. You can't go to a star and grab a piece of it and bring it home and run some experiments. All we get is the light from it. And so this entire history of astronomy, all we had seen was the light that we can see from our eyes, all combined together. But by using prisms and diffraction gratings, astronomers can now break up the light into its component colors. And what's amazing and revolutionary about this is that specific elements glow in specific ways. Not every element lets out the same kind of light. And elements absorb light at very specific colors. So for example, in this diagram here, you might see the spectrum of the sun, a star that emits at all wavelengths. For example, if you put up a prism to sunlight, you see a full rainbow. But if you look really closely, you take the sun, you put it through an even bigger prism, and you look closely, you'll see there are actually small gaps in the spectrum. And those gaps in the spectrum correspond exactly to the same lines you get if you take those elements and you put them in a heating lamp. So if you take a piece of sodium and you burn it, you put it in a flame, it produces this brilliant yellow-orange flame. It's a pretty cool experiment. And if you put that light through a prism, you don't get a rainbow. You just get one single line, a single color. And that's the exact color that's missing from the solar spectrum. So what this tells us is that in this example spectra, there's a cloud of hydrogen, sodium, and calcium between us and the star. All of a sudden, astronomers are chemists. We can figure out what distant objects are made of, how much of the stuff they have. It unlocks a whole new world. And so by combining these two things, spectroscopy and photographic plates, we're able to go beyond our own Milky Way. For the last 100, 200 years, we were focusing on completing the solar system. Now it's time to complete the entire universe, speed run, in 100 years. So some really important groups of people that contributed to this were the Harvard computers, who honestly deserve a presentation of their own. They're pretty amazing. It was a group of all women astronomers working at Harvard who meticulously pored over thousands of these photographic plates, basically going through and marking them and trying to find all sorts of trends. They did tons of amazing science. For one, they invented the stellar classification scheme, the way that we organize stars, that is still used by modern astronomers today. But one of the things they did is that they came up with a relationship called the Cepheid variable period luminosity relationship. Cepheid variables are a kind of star that pulsate. They blink on and off like fireflies. They get brighter and dimmer, and they do so at regular intervals. Now, lots of things in astronomy can get brighter and get dimmer, but not with this kind of regularity. What they showed is that how bright a Cepheid star is has a direct correlation with the period of its fluctuations. So a brighter Cepheid variable will fluctuate more rapidly, and a dimmer Cepheid variable will fluctuate more slowly. Now, there are only a few ways to figure out how far something is away. I mean, you can stick a ruler up to it. That works great for everyday use, but it doesn't quite work for astronomy. And so the method that we've been using since the ancient Greeks was called parallax. Now you can follow along at home with this one. If you stick your thumb out in front of your face, and you close one eye, and then you kind of switch really quickly which eye is closed, your thumb looks like it's kind of jumping back and forth, left to right. You just blink it back and forth. Now if you bring your thumb close up to your face, it appears to move a lot further when you do that process. So that's called parallax. What we can do is we can look at where stars are in the sky at either opposite ends of the Earth, or what you can be really clever and do is look at where stars are in the sky at opposite ends of a year. Remember, a year is the time it takes the Earth to go around the sun. And so by looking, for example, in the summer and the winter, you're basically measuring the parallax using the entire orbital diameter of the Earth to get that parallax. So that method was what astronomers used for millennia to figure out how far away these stars were. And it was pretty inaccurate at first, but as we got better and better, and as we got, for example, photographic plates, we could figure out pretty precisely how far away things were. Now, we have these parallax distances for these Cepheid variable stars, but we also know that Cepheid variables, we know their brightness because we can measure their period, the period luminosity relationship. And if you know how physically bright something is, and you know how far away it is, you can basically come up with a way, you can compare that with its relative brightness in the sky to give you a sense of how exactly bright the object is. So we call it absolute magnitude versus apparent magnitude. So for example, the sun is by far the brightest thing in the sky. It shines up the whole planet, right? But the sun is not the brightest star in the universe. And obviously the reason for that, the reason the sun looks so bright is because we're so close to it. It's apparently bright, but it's not absolutely bright. And so we were able to figure out exactly how absolutely bright these Cepheid variable stars were. And with this new period luminosity relationship, we could look at Cepheid variables in other galaxies. Now, until this point, we didn't know if other galaxies existed. We thought it maybe the Milky Way was everything. The Milky Way was the whole universe. But an astronomer named Edwin Hubble, along with his collaborators like Vesto Slipher, started to look at Cepheid variables in the Andromeda galaxy. And the distances he calculated proved that Andromeda was a completely separate galaxy. This shattered the view that maybe if the Earth isn't the center of the universe, maybe the solar system is. Well, all of a sudden we know that we have this celestial companion that's at least roughly on the same order of magnitude as our Milky Way is. It turns out Andromeda is actually bigger than the Milky Way. And there's one more amazing thing to come out of this. Hubble measured what's called the redshift of Andromeda. And the redshift is basically, redshift you know from when an ambulance passes by you. We call it the Doppler shift for sound. When you hear an ambulance pass, you hear the tone go up, and then as it passes you, it goes down, right? And that shift occurs for light too. So when a light source moves towards us, its waves, the waves of light, get physically squished together, and it looks bluer. When a light source moves away from us, the waves it emits get stretched out. It looks redder. And so by measuring this redshift and blue shift of a source, we can figure out if it's moving towards us or away from us. And what Hubble discovered is that as he was looking at all these different kinds of galaxies, the galaxies that were the furthest away were moving away the fastest. So the further you are away from us, the faster you're moving away from us. And what this shows is that the universe is expanding. It's not just that galaxies are kind of moving away from each other at random. Space itself is expanding. Space is stretching, being diluted, being pulled apart. And everything else in the universe is moving away from everything else. It's the Big Bang. And this is an image of what we call the cosmic microwave background, the faint echoes of the earliest light we can see after the Big Bang. This light used to be extremely energetic, maybe even something we could see with our own eyes, or ultraviolet light that would sunburn us. And it's constantly bathing all around us. And the reason we don't get cooked to a crisp immediately is that because the universe is expanding and stretching, that earliest light has been stretched out too, and is now in the microwave and radio waves. And so now, we're in the era of modern astronomy where we have telescopes like the Hubble Space Telescope, and even the James Webb Telescope, which looks at the infrared radiation that we feel as heat. So in this modern age of astronomy, we're looking to all these different wavelengths, going beyond our senses, and trying to capture as much information we can to understand everything we can about the universe. Any questions on that segment? Well, great. Now I just want to talk a bit about some of the cutting edge, some of the most interesting research that's going on in astronomy right now. And perhaps the most fascinating research that's going on right now is on exoplanets. At least some of the most interesting research is on exoplanets. Exoplanets are planets around other stars. So the solar system has 8 planets, and people have hypothesized for a long time that there are probably planets around other stars. I mean, there's no reason why they shouldn't be. We've known for a long time that stars outside the solar system can be similar to the sun, almost exactly the same. So why shouldn't they have planets? And it was only in 1992 when we first confirmed this. Now, that seemed strange to me at first. When I first learned that, I was like, why did it take so long? Now, there are 5,470 exoplanets confirmed, which also kind of seems like a low number to me. I mean, it is a lot, but you would think that with, trillions of sun-like stars that we see in the Milky Way, why aren't there more planets that we can see? Oops. Sorry, that was an accidental reordering. So the reason is there's a few difficulties with finding exoplanets. For one, the host star of an exoplanet system can be billions of times brighter than the exoplanet. And so it literally outshines any possible light that you could see from that exoplanet. In addition, exoplanets don't glow on their own. They're not stars, they're just like Earth, and Earth doesn't glow in visible light. So even if you point a telescope there and you could somehow remove all the light from the star, you probably wouldn't see very much. Exoplanets also can have extremely long periods. I mean, think about trying to observe the Earth. You might see the Earth once, and then it goes away for 365 days, and then only then do you get a chance to see it again. So you have to get really lucky to see an exoplanet. And in addition, we can really only see the biggest and closest planets to the stars. Like I said, all these difficulties mean that if you're looking for an exoplanet, you want to look for a large planet that's either close to its star, so it blocks out a lot of light, or far away, so it's kind of away from the star's light. And so why should we study exoplanets? Well, there are a lot of implications. For one, a science reason, exoplanets can tell us about the history of our own solar system. How did the Earth form? How did the gas giants form? Why are there 4 rocky planets in the center and 4 gaseous planets towards the outside? It's an interesting question that we don't really know the answer to yet, but by studying exoplanets, we hope to get a better picture. But more interestingly, and more philosophically, exoplanets might be a future home for humanity. Maybe if the Earth goes under someday, we'll need to leave it and find somewhere else. Or maybe the future of our species lies in exploring far away and distant star systems. Exoplanets might also host extraterrestrial life. Aliens, yay! It might be more mundane bacterial life, but it could be intelligent life. And just the prospect of that has been tantalizing astronomers, scientists for decades. I mean, that would be the biggest scientific discovery possibly of all time. The discovery of other intelligent life would immediately change everything we know about ourselves and our place in the cosmos. And so just for reference, I want to show you, this is a scale of the solar system. So these are all the planets with their correct relative sizes. And, Jupiter is a fairly large planet. You can see, compared to everything else, it's huge. And yet we could just barely, with the most advanced detection methods, just barely detect Jupiter if we were in a different star system. So you imagine, there's no chance that, we'd be able to find Earth. Imagine, we're looking at all these star systems, wondering why we can't see these planets, but maybe we're finding some Jupiters, but it's no wonder we can't find something that's like the Earth. So I want to talk about a few methods we use to find exoplanets. Method 1 is called radial velocity. So that same Doppler shift I talked about before, that causes light to get red when something moves towards us, and blue when something moves away from us, can be used to find exoplanets. And this was the earliest method that was used to find exoplanets. Like I said, think about passing sirens or cars. As something moves towards you, it gets higher pitched, high frequency. And as it moves away from you, it gets lower pitched, low frequency. So towards blue, away red. Now, most of us, when we think of a planet orbiting a star, we just think about the planet pretty much blindly going around. But that's not exactly true. The planet tugs on the star just as much as the star tugs on the planet. And so whenever you have 2 objects in space, they orbit each other around a common center of mass called the barycenter. And so a large planet orbiting a star will actually cause the star to kind of wobble. And as the star wobbles a little bit, sometimes it'll be moving towards us, and sometimes it'll be moving away from us. And so you can see the star getting redder and bluer as it orbits this combined center of mass. And so this method, radial velocity, can actually tell you how big the star is and how big the planet is, because it utilizes this fundamental fact that the star and the planet orbit the common center of mass. And so you can see that visualization on the bottom there, using those spectral lines from earlier. You can actually see them move left to right as that exoplanet orbits the star. Here's another visualization showing how the star and the planet orbit each other. Now in the solar system, this isn't really noticeable for our sun because none of the planets are really massive enough to cause the sun to wobble very much. In fact, the sun's barycenter, this barycenter of the whole solar system, is just outside the surface of the sun, and it points towards Jupiter, which is the second most massive thing by far. So the sun and Jupiter kind of do this, but all the other planets have a really negligible effect. So there's pretty much no chance that an alien species could detect Earth using this method. But one method they could potentially use if they were as clever and smart enough is the transit method. And the transit method is pretty much what it sounds like. A planet transits or passes in front of a star and blocks out some of its light. Now it's not going to block out all of its light because the planet's smaller than the star, but if you measure how bright a star is over time, you can see this characteristic dip in brightness. And this actually tells you the radius of the planet. So if you combine these two methods, you can get the radius of the planet and the mass of the planet, and that can give you information about how dense it is. Is this planet rocky or gaseous? Is it like Earth or like Jupiter? And this has been the most successful method so far. The transit method has discovered roughly 4,000 to 5,000 exoplanets. The radial velocity has only discovered around 1,000 exoplanets. But there is one problem with the transit method, and in fact, it's an issue with the radial velocity method too. And I want you guys to think, you need a planet to block the light from a star or somehow wobble it. Is there any sort of fundamental issue that you could think of with this method that might make it difficult to find exoplanets?
Got to be in the same plane that we are.
Exactly. You have to be in the same plane, right? I mean, if this is the star and this is the planet has to be orbiting exactly like this. If it's orbiting like this, it's not going to block out the light. And so these things have to be inclined just perfectly. And depending on how big the planet is compared to the star, there's only around a 1% chance to a 0.5% chance of that happening. And so we do miss out on a lot of exoplanets using this method. But that's where we use a lot of huge sky surveys to try to take pictures of all this enormous portions of the sky to try to basically get as many chances as we can to find those perfectly inclined systems. And that visualization on the last slide is a little bit idealistic. This is kind of what the data usually looks more like. Very noisy, because the star is fluctuating in brightness, there's turbulence in our atmosphere, and a star oftentimes has multiple planets if it has them, and so you get multiple dips and all this sorts of stuff, and it's kind of a mess to try to sort through it. But this is what astronomers are doing on a daily basis now, trying to confirm these exoplanets. And I want to show, actually, this is some data that I took myself as part of one of my astronomy classes. So this is not a new exoplanet, this is one that's already been confirmed. But my team basically went up to a telescope and took this data, and the points in gray are the actual light that we measured coming from a star. And as you can see, it was pretty much flat, and I can attest it was flat for several hours. And at some point, it just suddenly dipped, bottomed out, and then went back up. And so what's really cool is that using the data that we took, we were able to fit a model to it of what this planet might have looked like. And we were able to figure out its radius and all sorts of parameters like that. Pretty amazing stuff. Now, one of my friends in college is actively researching exoplanets, and so he uses an interesting method called direct imaging, where you literally actually do try to take a picture of an exoplanet. Now, I told you before that that's pretty much impossible, and for the most part it is, but if you use some really clever stuff, for example, on the left here I have a picture of the Large Binocular Telescope, the LBT in Arizona. The LBT is equipped with a device called the coronagraph, which can block out the light from a star really precisely. And using all sorts of math, you can kind of extract the tiny, tiny bit of light that is being reflected off of the exoplanet by the star. Even though the exoplanet itself isn't glowing, it is reflecting some light. And we can actually look for that and take a picture. So that's a picture that one of my friends kind of reduced from this data from the LBT. Really cool stuff also. And these are two of the kind of preeminent observatories that are finding exoplanets now. TESS and Kepler. TESS is the more modern of the two, the Transiting Exoplanet Sky Satellite, Survey Satellite. And then the Kepler mission on the bottom right. These are combined, these spacecraft have found over 3,000 exoplanets. So amazing work that they've both been doing. And I mentioned that we tend to favor finding these larger exoplanets because they're just bigger, they make a bigger signal. But over the years, as we've been looking, we've been able to find some exoplanets that truly are like Earth, as you can see labeled rocky planets there. And a few hundred of them are even in what we call the Goldilocks zone of their planet, where liquid water can exist. Liquid water means it might be possible to have life like on Earth. So this is one of the most impressive and interesting, just kind of modern facets of astronomy, in my opinion. Now you might see on the list there that there's an option called pulsar timing, and I'm going to get back to that later because it kind of ties into my next little bit of cutting-edge research. But before I move on, any questions on exoplanets?
How long did the survey take you to get the data for that one exoplanet?
Yeah, so we didn't do a survey because, like I said, this was already a known exoplanet.
Yeah.
We were basically just trying to observe it and then confirm its properties. So what we did is we used a resource called the NASA Exoplanet Archive, which is a giant list of all the exoplanets. And we found one that would be expected to transit at the time that we were able to observe. So we kind of narrowed it down to a few candidates, and then that one seemed like the best bet.
Is that like a Jupiter-like planet, or is it smaller?
Yeah, that one is like a pretty relatively large planet. We don't know the exact mass or anything because we used the transit method. But in terms of relative size, it's sort of I think they call it a hot Neptune basically. So it's not quite as big as Jupiter, but it's roughly on the scale of Neptune, and it's very close to its host star.
Is that a part of JWST that is being used for the direct observation of exoplanets?
Yeah, so the James Webb Space Telescope is looking at some exoplanets. It's not the best telescope for the job because James Webb is basically really good at looking extremely closely at a small piece of the sky. And so, like I said, exoplanets, there's very few of them. So when you want to discover them, you need to kind of do a whole sky survey. But what James Webb is really good at is looking at exoplanets we've already found and kind of digging in deeper. And so one of the things it does is, like I was talking about spectroscopy earlier, breaking the light into rainbows and figuring out what elements are there. Some astronomers have been recently using James Webb to take spectra, or take data using spectra, from exoplanets. And so we've actually recently found some really interesting features on some exoplanets. And so a team at the University of Arizona, where I'm at right now, discovered sand in the atmosphere of an exoplanet for the first time, which is pretty cool. I mean, it's just weird. Maybe this exoplanet is covered in beaches, just like some of the beaches here. And they've also discovered carbon dioxide and water in exoplanet atmospheres. So really cool stuff that they are basically looking for, things in the atmosphere.
How do they know that it's a lava world that you showed on that one screen?
Yeah. So lava world, that classification basically comes from its period. And so in astronomy, there's kind of this rule that's basically when the physics tells us that the closer something is to a star, the faster it has to orbit. So if you think about it like Mercury, the closest planet to the sun, orbits faster than Earth, and the Earth orbits faster than Neptune, the furthest away thing. And so these planets have a really short period, and so that actually directly tells us how close they are to the star. And we can look at the star and figure out its temperature and how big it is and stuff like that. And so we know that if this world was this close to the star, it would essentially be being cooked by the star constantly, and surface would be lava or, extremely irradiated at least. And that goes for all the other classifications too. Like ice giants, we know they're ice giants because they're far enough away from the star. And like hot Jupiters are like Jupiter, but so close to the star that they're hot. Yeah. Oh yeah.
What is in the corner of that graph that they have frontier? What does that mean?
Yeah, so frontier basically means that that's kind of the edge of the kinds of exoplanets we're trying to find right now. And so if you look at where that region of the plot is, it actually kind of corresponds with that bias I was talking about before, right? We look for big exoplanets. And for the transit method, you look for big exoplanets that are close to the star. Because the closer you are to the star, the more light you can block out, right? I mean, if I put my thumb to the sky like this, I'm not blocking out any light for anyone else. But if I'm right next to the sun and I put up a huge shield, I could actually block sunlight. So the transit method has been the most successful so far. And so it favors planets that are closer to the star, so on the left side of the graph. and it favors bigger planets, so higher up on the graph. So now the kind of mystery zone is small planets really far away from the star. And there's nothing really like that in the solar system. I mean, everything far away from the sun is a gas giant. So it's kind of a mystery. Do these planets exist? Are they in other systems? Or maybe they just don't form at all? And that's what that frontier is. All right, I can go ahead and, do we have time for one more kind of these sections?
Go for it.
All right.
Thank you.
And so the last thing I want to talk about is gravitational waves. And gravitational waves are literally ripples in space-time. So what do I mean by that? Einstein's theory of relativity was a slight modification to Newton's theory of gravity. Now, Newton's gravity is correct for most situations. I mean, everywhere on Earth it's correct. It describes the motion of the planets for thousands of years in advance. It's pretty much perfect. But we started to notice some weird deviations from Newton's gravity in very extreme environments. So one that's kind of relatively famous is that Mercury's orbit around the sun is not constant. Now, I already told you that planets don't orbit in circles. They orbit in so-called ellipses, kind of like egg-shaped or slightly oblong circles. Now, if Newton's gravity were completely correct, these ellipse orbits would be constant. Planets would just keep going around and around like this. But Mercury's elliptical orbit actually does something we call precession. It turns like this. Weird. So we had known about this for a while, but we couldn't really explain it. And it turns out that gravity isn't quite what we thought. Newton's theory is almost exactly correct, but Einstein's relativity modifies it just slightly and perfectly predicts things, like the precession of Mercury's orbit. Now, the reason we didn't know about this beforehand, and the reason Newton's gravity appeared correct, is that relativity only kicks in for extremely massive things. So the sun is pretty massive, but even its mass only produces a minuscule effect, which took a long time to notice, this precession. And so only when you get to objects like neutron stars and black holes, the true monsters of the universe, the densest things, most extreme things imaginable, that relativity starts to really kick in. But, up until recently, we didn't really know about all those objects, and so there was no need to modify Newton's gravity. But one thing that relativity predicts is that space, the 3D space that we walk through, and time, the time that passes, are not separate, but deeply connected. And when you move through one, you're moving through the other. And if you change one, you're changing the other. And it turns out you can actually make ripples in space-time. And in fact, you're doing so right now. Don't freak out, it's okay. You're making very small ripples. But it's true, whenever anything accelerates, it makes ripples in space-time. I'm making ripples right now, but they're just extremely, extremely small. Now, Einstein's relativity, once Einstein's relativity was confirmed, Einstein kind of predicted this phenomenon should exist, these gravitational waves, these ripples in space-time itself should exist. But he thought that they would never be detected because they would be too small. But amazingly, we got the first detection of gravitational waves at an observatory called LIGO in 2017. And I'll talk about how they discovered it. And that kind of also leads into a new discovery that was very recent called nanograv, which came out on just June 29th, just last month. So this is really fresh stuff and really exciting. But let me talk about LIGO first, that first discovery. Oh, I had the date, I'm sorry. The year is actually 2015 that gravitational waves were first discovered. Okay, so here's the LIGO Observatory, and it doesn't really look like much, but basically this is an observatory that's made up of a pair of 2.5-mile long arms. So these are really, really long arms, and they're very precisely crafted to be extremely straight and narrow, and what LIGO does is passes a laser through these arms. Now, it doesn't pass two lasers separately. It actually takes one laser and splits up the beam, sends the beam racing down these two arms for kilometers and kilometers and kilometers. And then the laser beam comes back, racing kilometers and kilometers until it comes back. And then it bounces again and again, and it bounces up to 280 times. So it travels the equivalent of like 1,200 kilometers before finally these two beams come back together and interfere. Now, you might have heard in like high school physics, or you might have heard just in general before, that whenever you have two light waves, if they're in phase, if you have the peak of one wave next to the peak of another wave, they constructively interfere. Or if you have a peak and a trough of different waves, they destructively interfere. Now, LIGO is precisely tuned to measure this interference, and it's set up so that At rest, when nothing abnormal is happening, you get perfect destructive interference. And so if you put a light sensor at the very end of the whole apparatus, you see a whole lot of nothing. The light's designed to perfectly cancel itself out. This is another picture of the apparatus. Laser splits the beams up and they reflect a bunch, and then they go back to the screen there, and the screen is where they measure that interference pattern. And here's a visualization of the interference. So as you can see, as a peak goes above a peak, the signal gets stronger, and as a peak goes below a trough, it cancels itself out. Now, LIGO in particular is looking for a very interesting interference pattern. It's not a simple one, but it's a very specific one. Another cool visualization of interference. It's looking for something like this. This is a picture I took in one of my physics labs where I recreated the exact experiment on a small scale. Now, my purpose wasn't to measure gravitational waves, but I was demonstrating the same concept here. So what this shows is the interference pattern that you see normally. Now, what happens is if a ripple in space-time moves through the observatory, this ripple is literally changing, it's slightly warping space and time. And so if a wave passes over, it stretches one of the arms of the detector, literally makes it bigger, and it shrinks on the other arm of the detector, it literally squeezes and compresses it ever so slightly. And as this wave washes over the detector, it stretches and squeezes the arms so that the light is no longer traveling in the same way, and the light beams no longer cancel out, and you see a signal. And so in 2015, after searching for a long time, decades after Einstein had predicted that these waves might exist, LIGO measured the exact signal that would be predicted by general relativity from two black holes, two monsters of the cosmos, many times the mass of the sun, spiraling into each other. Now, if Newton's gravity was correct, if two black holes were spiraling, they would just keep orbiting forever. But these black holes didn't keep orbiting forever. They let out energy in these gravitational waves, churning the ocean of the cosmos, sending out ripples in space-time, orbiting faster and faster until they merge together, sending out tons of energy. And for the last 20 milliseconds of their merging event, an unfathomable tiny fraction of time, 20 milliseconds, for that last 20 milliseconds of their merging event, the amount of energy that came out in gravitational waves from these black holes is more than all of the energy emitted by all of the stars in the entire universe. And yet this energetic collapse creates so much energy, but it spreads out over light years and light years of space. And so it's extremely dilute by the time it reaches us, to the point where these arms only change by a few nanometers. These kilometer-long arms only shift by a few nanometers. But we saw it. And in 2017, amazingly, we saw the same thing happen with merging neutron stars. Neutron stars being the second densest things in the universe after black holes. Now, black holes suck up all the light that reaches them. We can't see them at all directly. But neutron stars we can see. And so what's cool is as these neutron stars merged, we saw their gravitational waves. And just 1.7 seconds later, we saw a gamma ray burst. Gamma rays are like the light that you and I see, but squished together, extremely energetic, the highest energy light that we can imagine. And we saw a burst of gamma rays just after this merging event. And so this pretty much confirms that gravitational waves are correct. Relativity, another confirmation of Einstein's theory of relativity. And this is really a new era of what we call multi-messenger astronomy, combining the powers of light and other particles, things like gravitational waves, and particles like neutrinos. The neutrino is a particle which can travel through a light year of lead without interacting with anything. It's an amazing particle, which also deserves its own presentation. By combining these different parts of astronomy, we hope to be able to see back to the very Big Bang itself and probe the earliest physics possible. And so finally, I want to address the recent discovery regarding gravitational waves, which was called nanograv. That was the name of the collaboration that made this discovery. So LIGO, this observatory I've been describing, found this individual event, this individual massive gravitational wave. But astronomers and physicists have thought for a long time that the same relativity that predicts these waves also says that we should be absolutely swarming and buzzing with waves, just like that cosmic microwave background I told you about earlier in the presentation, which at one point would have cooked us to a crisp, but has been stretched out by the expansion of the universe. So just after the Big Bang, we should see all sorts of violent ripples in space, these gravitational waves, that would have been stretched out by the expansion of space into a low humdrum that pervades the entire cosmos. So we want to see, can we observe these low frequency gravitational waves, these extremely faint, dilute gravitational waves? Because if we could, A, that would tell us something about huge black holes in other galaxies, and B, that could let us see all the way back to the earliest moments of the universe's history. So to do this, we look at pulsars. You see an image of a pulsar there, a visualization. Pulsars are a type of neutron star, the neutron star being the second densest thing after black holes. An extremely dense object. Now, a neutron star is also formed from the collapse of an enormous star. An enormous star is spinning, and you may have seen, like in the Olympics, when an ice skater is spinning, and they pull in their arms, they start to spin faster. They're spinning like this, and they pull in their arms, and they speed up, and then they slow down. Well, the same thing happens in a star. As it collapses, it starts speeding and speeding up until once its tiny, tiny core remains. This core is literally the size of a city in some cases, the size of Manhattan or something. It's a tiny core coming from a giant star. It can be spinning insanely quickly, sometimes more than 1,000 times a second. And these extreme objects sometimes have these jets that shoot out at either end, like a lighthouse beam. And so astronomers can look for these lighthouse beams, swirling and spinning at dizzying rates. And these are some of the most regular clocks we have in our universe. They're extremely regular, pinpoint precision. But what's interesting is that if a gravitational wave comes between us and one of these pulsars, it'll stretch the space and squish the time, or stretch the time and squish the space. And we'll see this regular lighthouse beam deviate ever so slightly from what we predict. And if we look at pulsars all across the sky, we can try to map these gravitational waves. And so that's exactly what the NanoGrav collaboration did just last month. It used radio telescopes from all around the United States, radio telescopes that look like this, basically giant satellite dishes, to look for radio signals from pulsars. And they monitored 60-odd, some of them, and looked at their period, and this newest data release combines over 15 years of data of these pulsars, regular ticking timepieces and just slight deviations, and they found a signal that is completely in agreement with the gravitational wave background that would be expected. It's amazing, an amazing result. Now, the work is not done yet because the result they announced has a significance level of 1 in 1,000 or 1 in 10,000, depending on the test you use. So what that means is the chance of this signal being by just pure random noise is 1 in 1,000 or 1 in 10,000. Sounds pretty good. I mean, I'd be willing to bet on that at the casino. But scientists want to be more precise. And so a lot of times for these really groundbreaking discoveries, scientists are looking for what we call 5 sigma precision. We want to be sure to 1 part in a billion or more. And so it'll take more time and more analysis before we get there. But with international collaborations, bringing in data from South Africa, India, and Europe, and their own gravitational wave programs, we're hoping to get to that level within the next 5, 10, or maybe 15 years at the latest. And yeah, that's pretty much all I have. Thanks so much, guys. If you have any questions, I'll be happy to take them now.
Was it predicted or expected that gravitational waves would travel faster than gamma radiation? And what's the basis of that?
Yeah, so gravitational waves, as we understand, travel at the speed of light. The speed of light, we call it the speed of light because that was the first way we measured it. It was looking at light and how fast it moves. But the speed of light is actually more general than that. It's really the speed of information. If I want to communicate with you, the fastest possible way I can do it, no matter what, is the speed of light, whether I'm using light or gravitational waves or anything else. Now, the reason the gravitational waves arrived a little earlier than the light is for a few reasons. One, the speed of light is kind of a bad name because it's only the speed of light in a vacuum. And so if light is in air or water or anything else, it travels more slowly. Light can also be blocked. So for example, as these neutron stars were spiraling together, they throw up, you can imagine they're throwing up huge clouds of gas and dust. It's a very violent event. So that kind of blocks the light to some extent. And then also the part of that process which creates the gravitational waves and the light energy is slightly different. So for example, you have the spiraling that's creating the gravitational waves, and then the neutron stars actually finally merge together and explode, and that's where the light comes from. So those are a couple of reasons why those signals were at slightly different times. Yeah.
Does the nanograv project have anything to do with like looking at what is dark matter?
So as far as I know, it's not directly involved with dark matter. Now, there is one kind of interesting connection to dark matter, which is that some theories of dark matter posit that maybe in the very early universe, you could have actual dark matter stars. So to quickly explain what dark matter is. When we look at galaxies and we look at how fast the stars are moving in them, we can kind of see how massive they should be. So, like I talked about earlier, Kepler's laws of planetary motion, we still use them today in astronomy. And based on how fast the stars and galaxies are moving, we can figure out how much mass there should be there. But we can also just directly look at the galaxy, see how many stars there are, and count them all up, using computers hopefully, and figure out how much mass there actually is. And whenever we do this for any galaxy, we see there's a discrepancy there. The kinematics, aka how fast the stars are moving, tell us there should be something like 10, 100, sometimes even 1,000 times more mass than we actually see. So that's a discrepancy. It's completely untenable. And that's a very mysterious problem in astronomy right now. And we've come up with a lot of theories, but there's no explanation. That problem, that unexplained extra mass is dark matter. Now, there are lots of theories that people have proposed. So one theory of dark matter is called cold baryonic dark matter. And basically it says that there's some particle out there that we haven't observed yet. Maybe it doesn't interact with light, it doesn't obviously interact with gravity, and maybe it just interacts very weakly with all the other kinds of particles, so we haven't observed it yet. And in some theories, these dark matter particles might have clumped together in the early universe and produced dark matter stars. And if we did have these dark matter stars, they might have produced some kind of gravitational waves that we could observe. So that's considered one possible source of the primordial gravitational waves from the earliest moments of the universe.
You said they got the pulsar experiment, they got a signal that's consistent with the gravitational waves they would expect. What's the signal a form of, like, what format is that?
Yeah, so I should have put a plot of that in there. I can pull it up real quick and I can show you after. But basically what that plot looks like is you look at the angular separation of pulsars in the sky. So angular separation is like, this is 0 degree separation, opposite ends of the sky is like 180 degree separation. So you look at how far separated every pair of quasars is, every pair of pulsars is, and you can actually figure out, are these like weird variations in the timings of these pulsars, are they related to each other? So if you have a single gravitational wave rolling over the entire fabric of space, like it passes over a solar system and out the other side, or it passes from here to there, and it intersects like 4 or 5 pulsars, you should kind of see them change in the same way. Not at the exact same time, but at similar times. So we call that a correlation. And so what they made a plot of the correlation between the signals of the pulsar timing and their separation in the sky. And there's a very specific shape that curve should look like in relativity. And if you look at the data, it matches that pretty closely. So I can just quickly pull that up, and yeah, it's pretty amazing actually. Any other questions while I pull this up? Well, great. Thanks so much, everyone. I really appreciate you being an awesome audience. You guys